student choice for this week. What's the point of hyperspectral imagery? Okay, so there are a couple of questions around this on UCRU in the practicals and in emails that came to me as well. So on the left-hand side there, I've just got an image for you guys, which was one that I showed in the practicals. It's a small subset of an area in Litchfield National Park. This is a hyperspectral airborne image. And what you can see on the front face is just a standard false color composite. So trees are looking red because of that near-infrared reflectance. And then this is the way we display what we call hyperspectral data cubes. Okay, they look really pretty. They don't really tell you that much, to be honest. But it gives you the impression that there's so much more data behind that single face that you can see. What it's actually doing is around the edges is it takes just that line of pixels, okay? And then within that one pixel, it maps as a color the reflectance value in the different wavelengths, okay? So these wavelengths here would be the blues through to the greens, reds, and up into the near-infrared range. And same as we go this way, so blues, greens, reds, and near-infrareds, okay? And then the amount of reflectance in those wavelengths is shown by the color. So if you have high reflectance, you see a bright warm color, so those red colors, as opposed to low reflectance, which is the blues and into the purples. Okay, so you're getting a couple things coming through here. So our blues, greens, reds, and near-infrareds, low reflectance or absorption, and this is where our high area of reflectance is, where you get those the color is red. Okay, so if you imagine the spectral signature of vegetation, for example, you see that it's actually quite a low reflectance in the blue, green, and red area, and then high in the near-infrared. Okay, so these red peaks that you see here actually map down to individual trees as they line up on the edge of the image. Okay, so that's how you qualitatively analyze that particular image. Okay, so there's a few things in it, but really all it's telling you is information about just that one line of pixels around the edge of your image. So it really is just pretty. Okay, but getting back to the point of why do we want hyperspectral imagery in the first place? And the question was raised because you can still only view 3 bands of image at any one time on the face of your image. Okay, so I'm still viewing it as a 3-band image there. Although I've got 200 options, I still only see 3. So this is an example of a spectral curve that's been taken out from a piece of vegetation in my image. So you can see that although the image only allows me to see 3 bands at once, I still have the full spectral data there. Okay, so I can choose to display any 3 bands that I like, but all the data are there. And this is key because while you display whichever bands that you like, this is purely for your own visual analysis. And when we're working with the data on the computers, we actually want the computer to do the work for us. So the computer doesn't care which 3 bands you've displayed. That's just about how you perceive it. We can still process on all those bands of data. I can actually convert this image to a multispectral image, okay, and still make it look exactly the same in terms of its display. So you wouldn't, and with the exception of this 3D pretty look out the sides, if I converted that hyperspectral image to a multispectral image with the same wavelengths as, say, QuickBird or Iconos, it would look visually the same as that if I display it with a standard false color composite. But the difference is, in my spectral curve, I now only have 4 bands to choose from. Okay? And this image, when it's hyperspectral, will allow me to measure things at a much finer detail in terms of that spectral curve, and then map it across the entire image. So I can measure just how deep that absorption trough is, how broad it is. I can look at very specific bands that I want. So maybe there's maybe a very specific absorption feature. Again, coming back to those minerals that we looked at in class. Sometimes they were really, really narrow features that were of interest, and that's where we need hyperspectral data. I guess then it also comes down to, do we need hyperspectral? So hyperspectral is really considering, say, more than 10 bands. And do I actually need more than 10? Or do I just want 10 bands in this particular area? The problem is, if I decided for my personal vegetation mapping project, yeah, I just want 10 bands in this area, so that's where I'm going to place them all, then your data set is really limited. So yeah, okay, it's great for my project, but the next person that wants to come along then would have to refly the whole area because they don't get the 10 bands that they want. So in that sense, hyperspectral data is not necessarily required, but because I still want narrowband data, I still may only want a few of those narrow bands, it's better to get the whole suite. So coming back to our standard vegetation spectral signature, and I just use vegetation here because it is quite simple to explain, but the same could be true for looking at water bodies or minerals. It comes down to understanding the features that you're interested in. So if I want to be able to measure the amount of pigments that I see in a particular area in an image, I need the fine detail around the blue and the red areas, okay? Because I know that that's where pigments, for example, chlorophylls, carotenoids, that's where they're absorbing, okay? So that's where I need a great deal of detail that this just simply doesn't provide me. Same with water, okay? I want to be able to measure just how broad that trough is, so how far across that is, but also how deep it is. And I can't do that unless I have the spectral data to support it, okay? So again, it comes down to how many bands do I want? Can I strategically place them? So to reduce the number of bands that I actually acquire. And how do I make it so that the data are useful for multiple projects? So if I have a look at the spectral response, okay, so this comes down to a slightly different question about the nature of hyperspectral and multispectral data. But what I'm looking at here is the response of different bands in terms of their wavelength for the QuickBird sensor. Okay, so I've got the blue band, green, red, and near infrared. Okay, so this is the area within the electromagnetic spectrum that the QuickBird sensor is sensitive to. And remember, it's only actually going to give us one value within each of those bands. Okay, and Patrice asked the question of, if we've got different sensors and they've got different spectral resolutions, how do we compare the two? Okay, so this is QuickBird.
And different sensitivity.
Yeah, and different sensitivity as well. And so QuickBird and Iconos have a really similar spatial resolution, for example. So we use both QuickBird and Iconos and GeoEye and WorldView for the high spatial resolution imagery. Okay, same sort of stuff that you see on Google Earth. But their spectral resolution and sensitivity is slightly different. So QuickBird in the solid line and Iconos in that dotted line. Okay, and so you can see that the bands are slightly offset from each other. Okay, there are actually different shapes in terms of the wavelengths that they're sensitive to. So Iconos here actually has quite a narrow peak and will favour a certain wavelength within that blue region, which is slightly different to QuickBird. Okay, so you still call it the blue band in both QuickBird and Iconos, but they're actually measuring slightly different things. So what does that mean in terms of when we get imagery from different sensors, and can we actually calibrate for that? So if I go back to my standard vegetation curve, again, wavelength on the x-axis and the reflectance value on the y. Now if I convert this spectral curve, first of all to QuickBird, and again that's the shape of the QuickBird sensitivities. If I convert it to QuickBird and Iconos is up here again, we see that first of all you lose quite a bit of the spectrum, but the lines are slightly different. If I zoom into that area, you can see that those spectral signatures of that exact same thing actually look different. purely because of the sensitivity of the sensors that I've used. Okay, so this red and the green line were derived from that white one based on the sensitivity of QuickBird and Iconos. So QuickBird in red and Iconos in green. So if you were to look at chlorophyll, for example, and you know that chlorophyll is related to the absorption around this area, around 675 nanometers, you actually might come up with a different value of chlorophyll within that particular plant based on the reflectance if you didn't calibrate between your two different sensors. So I can calibrate my ground data to my sensor, but can I calibrate one sensor to the other? So if I've got QuickBird and I have Iconos, can I compare the two directly, and how would I do that? So I pose this to you guys. I have two pieces of chocolate cake, or I have two blue bands. Once they become chocolate cake, can I tell what made them up? Can I tell the ingredients? Can I tell the volume of the ingredients? Not once they're already chocolate cake. Sorry?
You get people who are allergic to different things.
Oh yeah, okay, so test allergy tolerances. Yeah, okay, so I know this one's got egg in it because so-and-so had a bit of trouble. Yeah. So when you have a multispectral sensor, it has already become the chocolate cake. All right, it is already average data. So you can't go back to those individual bands or the individual ingredients. If I have a hyperspectral data set, I can convert it to the equivalent of Iconos or QuickBird because I'm averaging it out. But once it's already averaged, that's how the data were obtained. Does that answer your question?
Yes.
So it sort of depends on what your application is. So the question is really, if you're reading papers and one is looking at mapping vegetation with Iconos and one is with QuickBird, are they comparable? Or they've done a time series analysis. Date 1 was QuickBird and date 2 was Iconos. What are the differences that you might see? And it's a really challenging thing because as an image analyst, often you just get the data that you can. You don't have a choice. You just get what's available. And that may be QuickBird one date, Iconos the next. But if you are doing quantitative analysis, so extracting chlorophyll, that's when you have more of a problem. If you're doing land cover classification, as long as you're not extracting signatures from one and putting it into the other, it's not so big of a problem. But usually if you're doing straight categorical classifications, the differences between your classes are going to be greater than essentially the noise, the difference between those two sensors.